When observing the cosmos, the data we receive is rarely pristine. It is often buried under layers of static and interference before snapping into focus. Many editing programs allow users to boost contrast and tweak brightness until a picture looks good to the human eye. This is image enhancement, a subjective process driven by aesthetics. In high-stakes environments like the Hubble Space Telescope, visual appeal is secondary to restoration, an objective discipline rooted in mathematical proofs. Restoration treats degradation as a physical process. By understanding exactly how an image was damaged during capture or transmission, we can work to mathematically reverse that specific process. Maintaining the integrity of scientific imagery requires this mathematical objectivity. It ensures that any manipulation of the data reveals the original signal, rather than creating a visually pleasing artifact. A lineal equation defines every corrupted digital image. The noisy image, g of x, y, equals the pristine signal plus noise. F of x, y is the ideal untouched signal. Eta represents the noise factor, accounting for interference from sensor heat or transmission errors. The goal of any restoration algorithm is to accurately estimate this noise term so it can be subtracted from the captured image. Because different environments create different types of interference, a system must first mathematically profile the nature of the noise before it can safely remove it. Noise is not a uniform occurrence. It possesses distinct statistical signatures that determine which mathematical intervention will be effective. These are probability density functions, or PDFs. We use these graphs to map the behavior and spread of errors across an image. This chart shows Gaussian noise, the most frequent model for sensor interference. The pixel errors follow a standard bell curve distribution. By contrast, Rayleigh and gamma noise profiles are highly skewed, pushing errors towards specific intensity values rather than spreading evenly. Impulse noise, called salt and pepper noise, shows a bimodal distribution. Its histogram reveals two sharp spikes, where pixels are forced to absolute black or absolute white. Uniform and exponential noise patterns create their own distinct graph shapes in specific electronic environments. To be effective, a filter's mathematical topology must be explicitly matched to the noise's specific PDF. A universal tool often results in failure. When we identify Gaussian noise, the simplest mitigation strategy is the Arithmetic Mean filter. The filter moves a fixed window across the image matrix. It averages the pixel values within that local neighborhood, recalculating the center pixel based on the sum of its neighbors. In this X-ray comparison, Panel B shows the original image corrupted by Gaussian noise. Panel C shows the result after applying the Arithmetic Mean filter. While the noise is reduced, the image is now visibly blurred. Arithmetic averaging treats sharp structural edges and random noise exactly the same way. To improve on this, we can use a geometric mean filter. Instead of simple addition, it uses multiplication and roots to process the local neighborhood. The geometric formula penalizes extreme values more effectively. As seen in Panel D, this results in less blurring and better preservation of the hardware's structural details. Still, all linear spatial filters involve a compromise. To achieve noise reduction, the system must inherently sacrifice some high-frequency image detail. More advanced restoration uses the Contraharmonic filter. This introduces a variable order parameter, labeled Q, which allows the algorithm to target specific noise extremes. A positive Q value is engineered to target dark pepper noise. In this matrix, a corrupted black pixel is algorithmically replaced with a value of 99, derived from the local intensity.
Panels A and C demonstrate the successful removal of pepper noise from a degraded X-ray using this positive parameter. If the corruption consists of bright salt noise, flipping Q to a negative value allows the filter to target and remove those white spikes, as shown in panels B and D. Because this filter is so specialized, the operator must identify the noise profile with absolute certainty before setting the value of Q. If the wrong sign is selected for Q, the result is catastrophic. These images show the total destruction of the underlying data. Applying a negative Q to pepper noise actively amplifies the degradation. The resulting artifacts are mathematically more destructive to the image than the original interference. As filters become more powerful, the margin for error vanishes. Successful restoration demands an exact match between the filter's parameters and the noise's statistical profile. periodic electromagnetic interference presents a different challenge. Because it stretches across the entire image in repeating patterns, local spatial filters often fail to isolate it. Panel A shows a historical image of the lunar surface, obscured by heavy sinusoidal noise. The interference creates a regular grid pattern that masks the landscape. To solve this, we pivot the data. We use Fourier analysis to transform the image from spatial coordinates into the frequency domain. In the frequency spectrum shown in Panel B, that repeating grid is no longer spread out. It appears as these distinct symmetrical spikes of concentrated energy. We can then apply a band reject filter. This acts as a precise mask that targets those specific energy spikes while leaving the rest of the spectrum untouched. Once those frequencies are removed and the data is converted back to spatial coordinates, the interference disappears. The result in Panel D is a perfectly crisp lunar landscape. Translating data into a different mathematical domain allows engineers to neutralize systemic errors that are essentially inseparable from the signal in their original format. Static filters execute the same calculation across every pixel in an image, regardless of whether a specific pixel is clean or corrupted. If the noise density is too high, a standard static filter begins averaging noise with more noise. Even after 3 passes of a median filter, these panels show that significant interference remains embedded in the signal. Solving this requires a system with decision-making logic. This is the adaptive median filter. This algorithm tests if its local median is corrupted. If it identifies dense noise, it dynamically expands its sampling window from a 3x3 grid to a 5x5, searching for clean data to use as a reference. Conversely, if the algorithm finds the pixel is already clean, it leaves it untouched. This avoids the blurring penalty that characterizes older, non-adaptive filters. Replacing blind math with adaptive logic allows for the aggressive removal of dense noise without the unintended blurring of clean signals. True image restoration is guided by 3 directives: neutralize impulse noise, smooth uniform interference, and minimize the distortion of the original signal. There is no universal filter. Success relies on analyzing the specific degradation model and selecting the mathematical tool required to dismantle it. This process is never about aesthetics. It is a strictly objective method used to retrieve data that has been obscured by physical or electronic interference. When we capture data from the edge of the universe, we rely on these mathematical frameworks to ensure the information we receive is accurate. Image restoration combines statistical profiling with dynamic mathematics to extract the original signal from corrupted data, providing the foundation for our visual understanding of the world.